Hello everyone, welcome to Engineers Ireland and the Applied Maths classes. Today we're totally changing into stuff that'll seem completely different to what you've done before. Up to this you've been dealing with things where you break down forces into its components and you solve problems. What we're going to look at now are differential equations. They form a massive part of not just applied mathematics when you're in college and in profession afterwards, but in a whole range of subjects such as physics, engineering. It's really not possible for me to explain to you just how important these are as major tools in the toolbox that you will use when you're in college and in your professional life. I'm choosing to move into these now rather than dealing with let's say relative motion at the moment or oblique collisions. That's basically like playing billiards or snooker, in other words one sphere hitting off another sphere. I'm leaving those aside. We'll come back to them of course, and I'm doing it because this should hopefully be fresher for you. You should see it as being like a bit of light relief, we'll say, from the rest of the stuff. Now today we will look at differential equations. There's 2 chapters actually devoted to these in Connolly's book. Now I would hope to get through both of them today, because really what they are is they're showing you how to manipulate or wield these like the proper tools that they are. There are 3 related chapters then. One of them has to do with inertia, and that covers motion of a rigid body. It covers compound pendulums. Very interesting section. We will cover that after this one. There's also a section on circular motion and another one on simple harmonic motion, which is like the motion of a pendulum, or quite a range of things, a surprising range of things that actually occur naturally and also that are necessary, we'll say, in the mechanics that engineers and others actually develop. So then we'll get through these differentials now. We'll deal with those other 3 chapters, hopefully in 3 to 4 weeks in total, and you will have at that stage covered more than enough to answer all the questions in the Leaving Cert. However, it's always important to have extra questions just in case you get a hard one. And the second thing is, it's never wise to not complete a course, because that course is just a lower level on which new blocks actually are set, the ones for next year, the year after. So if you guys want an easy life in first year in college, I suggest to you you learn your applied maths, the whole course now, and take life easy next year and really enjoy yourselves. So I would think at this stage of 6th year you will have not only completed differential calculus but integral calculus in your maths classes. So then what we're going to do is learn how we can manipulate them and play around with them, almost the exact same ways you can do with variables in algebra. We're also going to set up what we need to know for the 3 chapters on circular motion, simple harmonic motion, and motion of a rigid body, and the compound pendulum. The practice you get from these is definitely going to help you in your calculus, both differential and integral, in your mathematics. So you actually win on the double here. Now to start with, for the Leaving Cert, we really just deal with first order differentials. Now fundamentally they're in the order of a dy dx. You will have seen that before. We're getting the d dx of y, some function of x. Now we do actually look at a second order differential, which is of this type of style, we'll say, of something, and we'll just say y at the moment. But we're only going to deal with ones of those that can actually be converted into a first order differential. So it may look like it's going to be a second order, but in one quick change we will convert it, and you will see why the conversion works. So let's start. Now, the Conliffe book, I think, is particularly good on calculus, on differential equations, because it actually gives you a series of style questions, and it's the exam questions from the Leaving Cert. Basically, they'll come from each, or from this group of styles. The thing is, once you see it in terms of a style, what do you do? And if it's a certain type, we do something. If it's a different type, we do what's appropriate for that type. You'll actually find that it's easy to step your way through this, and then you'll get amazed with the problems you can solve. For example, we have before been looking at projectiles, but it was explained to you that we were only looking at constant acceleration problems. That's where you either have no acceleration, or the acceleration is a single constant, therefore the velocities are going to change in a linear fashion. If we want to solve any other problems other than those really simple ones, we must turn to calculus, to differential equations. So you can see how this is an absolutely essential next step for you guys to learn. If we look at that's obviously straightforward mathematics that you have for your Leaving Cert, and you deal with each one of those. We are saying, I want to find y, okay? Now this is where the thing starts to look like algebra. Even though you may think dy dx, oh my goodness, this is very fancy mathematics, they are still little units that you can trade like stocks on the market, okay? We can obviously say that implies dy is equal to 2x by dx plus x cubed by dx plus sine x by dx. If I know that that is dy, what we do also know is that the integral of dy, which is y, that must be equal to each of those integrals. By the way, one of the nice things about the applied maths for the Leaving Cert is, once you've got around the workout the mechanism of the problem and set up your structure, the actual mathematics is generally easier than the mathematics that you will meet in the maths course. So you will find that many of the differential equations that we get here are actually quite easy to solve once you have mastered the standard in mathematics. Now, this is a general solution. Because we don't have, if you remember from your maths, we're not integrating from a lower to an upper bound, in other words over a range. We have to introduce a c. Now, the basic reason for this you can explain by way of an example. If I knew that dy dx was equal to some value, we'll just call it m, a constant. Differentiating something is actually getting a slope. So we're saying, that's a slope. Now if I integrate, I'll get y is equal to m times the integral of dx, which is equal to mx plus constant. If I plot that, we will say there's an infinite number of possible solutions. The slopes of all of these lines is m. So if we had only got mx, how would we possibly know which one of these lines that we're dealing with here, whether it's that one, or any one of the infinite number of lines? What we want to know is, where does it cross the y-axis? That'll be the c value. If we don't know what it is, we have to leave it as a variable. When we get something, an equation, and we haven't been dealing with limits, that's a general solution. Now, if I knew something, for example, y equals 0 when x is equal to 0, I can now actually go and put it into my equation and get an answer, and that then will give me a value for c, and that will be the specific solution, the one specific to the condition that you imposed on it, this guy down here. So you will see the reasoning is no different to the reasoning that you've had in your mathematics. We'll just learn terms that makes it easier to communicate to other mathematicians, applied mathematicians, engineers and physicists, such as specific solution, general solution. Now you will notice that I am writing a cross on the screen here. That simply says to ensure that I will not run out of space on the screen if I went directly down. You, in your copybooks, you should actually be working your way down the page rather than across the page. What you'll notice here is we've been forced to put in a C. That is our general solution here. If we were told something, condition, that y equals 1 when x is equal to 1, what we would then do is you'd say, going back to that equation, you'd say that implies y, which is log x plus c, 1 is equal to log 1 plus c. And that'll tell us that implies c is equal to minus 1. So we can say that implies y equals sorry, I should be using this one here, y equal to 0, and I will get c is equal to 0 just to keep life easy for us. We'll come on to the more complicated ones in a minute. I'd forgotten I decided to do this. So y is equal to log x, and there's no c in this case, and we will say that's the specific. Or particular solution. So you can see all we do is we knock out this variable that we've had to bring in, the coefficient, by knowing some condition, and in this case that. What's the first type? The ones, and these are the easiest ones, okay? Solve by separating. Now then, we can see that there is a y here. We have our x's over this side, so we would like to bring that over here, and we'd like to bring that over here, and that's very easily done. And if we integrate both sides, we can say that implies Now then, it's very important, and I know I keep saying this to you guys, and I've been saying it to people for many decades now. It's really, really important when you know that, for example, in this case, we're doing important things like differential equations, that we run the risk of just letting the easy, simple stuff slip by without taking care of it. Now, I consider that people are very fast to know that the ddx of sine x is cos x. Now, the reason I mention it is we're integrating here, and it would be awfully easy to leave this as cos x. In reality, the integral of sine x is minus cos. I'm just bringing it to your attention, and I know it sounds stupid, but when you rush, you're very likely to make this mistake here. You will just say, oh, 6 sine x dx, integrated, you'll get 6 cos x. You do not. You get minus 6 cos x. Okay? Now let's look at the particular condition on it. Now, the log of 1, which is 0, is equal to minus 6 cos pi plus c. That implies c is equal to minus 6. So the general solution then, or the specific one, the log of y is equal to minus 6 cos x minus 6. So, believe it or not, you're now playing with differential equations. The particular type are the easiest ones, and there's only about 4 different types, by the way. How do you know? Well, it's the same as in mathematics. Your job is first to look and see what's there. It's very clear that we can separate out that and move it across to the dy side. Inspection shows you that you can do this. Let's look at a second question on this particular one. Just choosing a suitable one for you guys. Yeah. There is an x here. We do have a y over this side, so we can easily deal with this. And we will say we can deal with whichever side we want to deal with first, okay? We're saying dy dx. I'm going to have a 1 over y squared here now. And that's going to be equal to 1 plus 2x squared all over x by dx. There is absolutely no sense in my going through the mechanism of integrating this for you guys, because I've mentioned to you that the methods of integration that you learn in your mathematics actually go well beyond what you need for this particular subject. So it would be a total waste of your time and my time to go through that. Now, if we were told y equals 1 when x is equal to 1, we will then find that implies c is equal to minus 2. So we've got our general solution here. And we can say that implies and you might call it specific solution. I prefer the word specific, but I think for the leave insert, particular is the one that you're dealing with. This particular problem is different to the first one we dealt with, because in the first one, okay, you had dy dx, but all the variable bits were x's. We've now moved on to a situation where you have parts of it deal with the y variable and parts of it deal with the x variable. So you just put like with like, and we now finish up with more interesting integration on that side, not just interesting integration on the x side. We know a few things already. We know that v equals ds dt. Now what does that imply? It implies that ds is equal to v dt. So the integral of ds is equal to the integral of v dt, which implies s equals the integral of v dt. Now that's nothing other than a restatement of that. But it's one of those nice things about mathematics, that something that's simple that you know already, if you just play around with it and show it in a different form, you actually get a useful tool to aid you. Now obviously the same thing holds for a equals dv dt. Acceleration is the rate of change of velocity with respect to time, so that implies dv is equal to a dt, which implies the integral of dv equals the integral of a dt, so v equals the integral of a dt. Again, that's just saying this. But knowing it straight up front means you don't have to think about it, and you can place it out and not waste time in your exam, because after all, you have two functions. One is to educate yourself into applied maths. The second one is to be able to perform in an exam, and to do that you have to be become quick. So when you see alternative versions of something you know already, whatever you do, don't dismiss it, because seeing the alternative version means you have something new and clear that you should be able to look for in equations that you'll be given, and in seeing the alternative versions you can often see your way in through to the solution. So what else did we know about this? A, we're saying is dv dt. If you remember from the maths, the chain rule is nothing more than multiplying something by 1, maybe several times, so it's by 1 by 1 by 1. So we will say, okay, that multiplied by 1 hasn't been changed, so what useful form of 1 will we use? As you can see, that's still just 1. Now, just like in the chain rule, what we can do is we can swap those around. Obviously 2 by 3 is equal to 3 by 2, so there isn't a problem here. And we know this. That's equal to v. So it's equal to v dv ds. This is really important, because without realizing it, you've actually managed to convert a second order differential into a first order differential, because we know this, a, which is dv dt, and we'll say what's v? It's the d dt of s, so it's equal to and that is just, now this is the important bit, this guy, which is a, we now know it's equal to v dv ds. This is one of the very cute, well, it's your introduction to one of the very cute things that happens all the way through as you move up through in learning your calculus. You'll often find that simple reorganizing of things that you know already can bring down the complexity of a problem. Rather than having to deal, if we were dealing with, let's say, a problem with d2s dt squared, and they're the kind of problems where we'll be given information on distance and we'll be given information on time and not necessarily any information on velocity, and you don't want to go to the problem of developing equations for velocity, you want to deal with distance and time. We may find that we could get ourselves into problems, and the problem would be we're dealing with a second order differential. Now that mathematical problem is best simplified down into this. So we'd say, okay, you may not want to deal with velocity, but if we do, we've actually got much easier mathematics. So fundamentally, that second option is always the better one, because you'd be amazed the amount of things that you go to try and solve with differential equations and the thing can blow up in your face. And the only reason it'll do so is because you haven't been smart with your mathematics. You haven't looked at it, considered what's there, looked to see if you can simplify it. Because as a basic rule, certainly for maths and applied mathematics for the Leaving Cert, they're not, the examiners and the department are not looking for sluggers. They're looking for thinkers. So almost always you will find there is a thinking solution that is much easier and shorter, and therefore you get ahead of your time curve and you have no time pressure in your exam. So let's have a look at some of these guys and what happens. Now, just a first little rule for you. Almost always in a question, in these sections, they will talk about some item, an object, a particle. They either will give you the mass of it or they won't. Now that's not being silly here. If they give you the mass of it, you should look in terms of force, because force is mass by acceleration. If they don't give you the mass of it, you actually produce your equations as acceleration equations. You don't have to think any more than that. Look for the mass. If there's mass in there, you say excellent, I'll deal with force equations. If not, you deal with acceleration equations, which is fundamentally force per unit mass. This particular object, the mass is 2 kgs. Okay, therefore we'll deal with force. Now there's a retarding force, something slowing it down. Therefore we would expect that this thing, when it hits the equations, will go negative. So it's 6 the square root of e newtons. Okay, The logbooks tell you what newtons are. And at a particular instant, that's the information that's given. Now, having got that information, they're now going to ask you a question or a number of questions. The wording of the question is really important, because when you look at the wording and you assess what's in it, it'll tell you which version of the acceleration equation you want. Are you looking at a dv/dt situation? Are you looking at one of the other two versions? It all comes in. In this case, it's find, and the important words are how long. How long it requires. That means we're looking at time. Okay? How long does it take to come to rest? This is a time-related problem. Because of that, the mass by acceleration that we're going to use we got information. We know it's a how long, so it's per time situation. We also know that we got velocity information, so we will use the dv version. So we're saying, right, minus 6 the square root of v. It's minus because it's a retarding force. It's slowing you down. Now notice that we do have another little piece of information. This is where our conditions come in here, okay? At a particular time, it's 9, okay? And we're saying we want to go and look at 9 to 0 in velocity. And we're saying note to time. We just want to find out the time. So that's bringing that in for v to the half, and this is bringing this guy in, v to the half. And we were saying, okay, it's 3t down here is just straightforward mathematics. You'll notice, like I've mentioned before, the functions are easier than you will actually find in general when you're dealing with differential or integral calculus in your mathematics. The real applied maths bit here is just really that. What we have done there is we have formulated our problem, okay? And it's done in that line. We're saying mass by acceleration. What version am I going to use? The how long does it take tells you it's a time problem. So we will use dv dt. If we look at another problem, we'll see how the question again that's been asked of you dictates what you're going to use. It says, and in this case it says, a body undergoes a retarding force. Now throughout the question it's not going to give you a mass, okay? So we'll just write that down as mass is unknown, okay? You wouldn't write that normally yourself. I'm just bringing this out to highlight a point, okay? And we say retarding force meters per second squared, and it comes to rest meters per second. The question is to find the distance travelled. So it comes to rest from that. So we're saying from 10 meters per second down to 0 meters per second. And we want to find the distance. This is a distance related problem. Now, an interesting thing about this problem is the retarding force, okay? So we're now saying to ourselves, okay, A is equal to V dV ds. ds, because we're looking at distance, okay? The question is telling you the form to put things in. And he's saying that's equal to minus V by 1 plus V squared. What you will notice is that V is cancelling that V here, okay? So we now have, I'll write it in a different colour for you. All of this stuff down here is old hat for you guys. That's the applied maths. When you recognize that the question that you're asked in the applied maths has two aspects to it. One is information, because you must have information or you can't solve the problem, and the second is, with inside it there is the actual question asked, which is like find the distance. there are key words in that question that will tell you what version of acceleration to use. Once you realize that, these are terribly easy. They are one of those sections in the Leaving Cert that you should be able to get full marks on, especially because you have, or will have, by the time you get to the Leaving Cert, practiced your differential calculus and integral calculus, and this in turn will also help your mathematics. I want to show you a slightly different situation. Now, first off, I'll just recap on something simply because Connolly in his book does. If you remember when we had problems in the constant acceleration situation where something was thrown up the way, anything. It could be a football, it could be a projectile of any sort. When it's been thrown up the way, we know, obviously, that mg is acting down the way. That's the force of gravity, which is the weight of the object. It's its mass by gravity. Now, what you had before was a situation where all of our problems were actually problems in empty space. There was no air, so there was no air resistance. Now, most people will have cycled a bicycle, or will have maybe wrongly put their head out the window of a car while it was moving, or run so quickly down a hill that you can understand this concept that's coming up now. Resistance, air resistance, it always pushes against you. If you are cycling in that direction, it's pushing this way. If you turn and you cycle back the way, it'll be pushing that way. So it's a bit like the resistance between an object and a surface. It always acts against the direction of motion. So what we now have is resistance. And again, if you cycled a bicycle, you will know that if you're just cycling slowly, you don't feel much air resistance. But if you cycle faster, you do feel it. And if you cycle much faster, you feel that the resistance has gone up, and it actually has gone up. Now, in general, resistance, it's proportional to the velocity you're doing to some power. Now, that power is often in the order of 2, so velocity squared. You could sometimes see it 1.8. So if resistance is proportional, that implies resistance is equal to some constant, where k is the constant of proportionality. And you will be given an expression like that. So this resistance here, which is, we're saying if the object is actually going up the way, so we're saying it's still going up the way, so the acceleration is in that direction, we can now say to ourselves that this guy is going to be negative because it's acting against, and this guy is going to be negative. If you now look at the situation where the object is actually going down the way, it has reached its peak height and it started to fall, we have this time that's positive because it's in the direction of the acceleration, but the resistance is still negative because it always operates against the direction of motion. Now, we're going to, in the next problem, just bring in resistance forces. There is a very interesting lesson to learn from this, because the example 3 on page 322 of Connolly's book shows you just how significant this is. we have a particle, its mass is m. It's thrown vertically upwards at v to start with, okay? Now, just watch on this particular thing, resistance. You can see that's the k we talked about, and in this case the n is 2, power of 2. Not an unusual one, but in this problem, and these are the kind of things you should always just watch for, what are the dimensions of this? What does it tell us about this? It's saying to us that it is in newtons, which is basically the measurement unit for force, but it's per unit mass. Now, because it gave it to us per unit mass, I can actually dismiss that when I just called it m. Now, obviously, if they wanted to know what total force was, you will bring it in afterwards. But my resistance is allowing me to get away with just looking at acceleration, because it's per unit mass. There's 3 questions asked to this, and it's what makes this interesting. 1. Find max height. That's telling you for part 1 the particular version of acceleration to use. The time to reach the maximum height. That's telling you which version of the acceleration equation to use. Now, the third one is what makes this particularly interesting. If no resistive force, how high and how long? So the part 3 says there's no resistive force. Tell me how high it gets and how long it took to get there. This is a particularly interesting little one. If you remember, in previous problems where we looked at items being projected vertically, we were able to use the 3 algebraic linear equations, the v equal to u plus ft, and the other 2 equations. In this part 3, because there's no resistive force, we know we have got a constant acceleration problem. The only thing that's really affecting this here is the force due to gravity, which is basically the weight of the object. That's the only thing that's that is causing a change in its state. So even though we're dealing with a calculus problem here, this part 3, you go back to your basic equations. Like I mentioned to you, our resistance, we were told, was newtons per unit mass. So I can actually just use an acceleration here rather than the force, because it's per unit mass. If I put in an m here, I'd have an m here, and they just cancel each other. So we're happy here. you just turn to the mathematics you're learning in your maths course. That becomes this. The range we're dealing with is 0 to 50 because the initial velocity was 50 and it finishes up stopped, so it goes to 0. We find that it took 26.2 meters to do that. Now the second half, or the middle bit of this problem, which is a straightforward one, we're going to use dv dt. Notice the dt this time because it's a time problem, okay? When we carry out that integration, we find that t is equal to 1.86 seconds. So that's fine. We know it took 1.86 seconds for this thing to get stopped. It had gotten 26.2 meters into the air, above the level of where it started from. What stopped it? A combination of two things stopped it. Its weight, which is the force due to gravity, and the resistive force. Part 3 of this question is asking, well, if we didn't have the resistive force, what would you get? Gravity is still affecting this thing. Its weight is still pulling against it. So how high did it get? This one over here, with the resistance force, and you notice it's only 0.05, which is 1/20th of its velocity squared. Not massive, massively huge, you would imagine. But if that was removed, if there was no resistance, how high would it get? Amazing. About 5 times as high. So you can see how enormous the impact of air resistance can be. It's extremely difficult to overcome. It's the reason why so much money is spent in the development of good aerodynamics for cars, for jets, planes, basically anything that gets propelled into the air or has to move through the air at any decent speed. You will notice that because it goes up by velocity squared, the faster you want the thing to move at that you're designing, the faster you want it to move at, the more dominant this particular factor becomes. Now, how long would it have taken? That's just v equals u plus ft implies t equals 5 seconds. So at this time it would have continued moving for 5 seconds. Prior to this it was 1.86. And in 5 seconds it would get just about 5 times as high up as it actually got with that air resistance. Now the nice thing is, there's only one more example. Once this example is covered, the type of questions that will come up straight on differential equations, their styles and the little idiosyncrasies that one question has relative to the other should be covered, which means that any of the examples in the book will be within inside your scope, and you have obviously between now and perhaps the second week in January to practice these. By the time you come back, if you've practiced these and you have got good at manipulating your equations, developing them and manipulating them, then we'll be in a very good position to start into the first of the three that uses differential calculus, and that would be the rigid body problems. Right, this time it's a car. Engine. So far, I know we haven't talked about work, energy, those concepts. We'll get onto those in about 3 sessions. In the meantime, if you just take it on faith, a little bit of this, you will actually get to see that all it is a new little dimension, an extra little layer that you can look at in relation to these things. But it's still, this is still an interesting problem, so I'm including it. And when you see how you operate in relation to work and the energy of something, you will be getting a little precursor to the chapter that we'll get onto in relation to the relationships between force, work and energy. Now, constant resistance, that's much more the kind of thing that you'd expect between the car and the ground. So we're basically looking at problems like the object sliding down the inclined ground problems that we looked at a while back. So this is a constant resistance one. It's not like the last one, which was dependent on the velocity, or actually the velocity to a power that the item was going at. Now, in this particular thing, it's giving you that information. Now, what is the question they're going to ask you? He's saying find the time. That's telling you what version to use. So, we can draw this. It is no way more complicated than any of the other type of problems you've dealt with. We don't even have to split our forces into components, so life is nice and easy so far. Now we're saying T. What is T? That's what we have to find out. Now, 42 kW, that's 42,000 of these guys. So then, you have a first glimpse at the relationship between work and force. Okay, so we're saying the force is equal to the work divided by the velocity here. So now we can say this is where we're using what we know from over here. T is 18 seconds. What did we do here? Just concentrate on the lower piece at the moment. We're saying acceleration. We're using dv dt. We're using it because it's saying find the time, so it's a dt problem. We have found this expression, which is 70 minus 2v over v for acceleration, and we found it up above here, and I'll come back to that now in a second. Once we've got this far, here on in, you've really done your applied maths. Now you're back into straightforward mathematics in this area here. We're just integrating, and integrating things that aren't even particularly difficult. So we get our answer. The key part to the applied maths is always the first little bit. That's why you should always read the questions very carefully. While your mind is calm, it'll see all of the bits of information that you've been given. There's rarely too many of them anyway for the Leaving Cert. And then you carefully listen to the question that's been asked, because that then tells you what version of the equation you're going to use, and that speeds you up a lot. Otherwise, you could be faffing around and trying different things and finding long, convoluted ways. Each of these problems so far, you have to be able to admit now, are straightforward. Easy manipulation and integration, followed by very basic algebraic mathematics. All we have to do is to set up the equations. Now in this case, because we were dealing with a work scenario, there are a few little things you need to see about this, just as an introduction to something we'll get onto fairly soon. Power. What are the dimensions of power? It's joules per second. What's a joule? It's a Newton meter per second. So that's the same as saying newtons by meters per second. Okay, that's the game. Meters per second, isn't that velocity? Newton is force, so we'd say power is equal to force by velocity. The logbooks give you the units for power, okay? Joules per second. It'll also tell you what a joule is. A joule is a Newton meter, okay? If an item has been moved by 1 meter operating under a unit force, we can say that's 1 joule, okay? The trick that we're playing here is we're using our dimensions to inform us on the relationship between power, force and velocity. Now because of that, we can obviously then just say that therefore force equals power divided by velocity. And that's where we got this. Because we were told that it worked at a constant rate of 42 kilowatts, okay? 42,000 watts, okay? Don't worry about that little bit of it, because we have a whole chapter that we'll come on to in about a month, where we will start to play around and show how power, energy, work, force, how all those relate to each other. I've always found it easiest to find the relationship by rejigging the dimensions. Once you know a joule is a Newton meter, you will notice it comes in as a Newton meter divided by seconds. But that's the same as a Newton by meter divided by second, and that's velocity. So you can actually find the relationships between each of these main things by looking at their dimensions and seeing how you can rejig the dimensions. That's the last of the questions that are explained in Connolly's book. They run through two short chapters, 19 and 20. They're straightforward, I think you have to admit it now. The secret is look for the key words. The first thing obviously is if they give you the mass of something, you generally expect to work with force. If they don't, you generally expect to work with acceleration. Sometimes, even though they may give you a mass, if they give you the force per unit mass, well, you can go back to the acceleration one again. Then if they say how long does it take, words like that tell you immediately it's the dt version. If they say how far or what distance, clearly it's a ds version that you're going to be using. And once you see those key things, you can go straight to the appropriate equation, and from there on in, much of the playing around, once you've gone through one or two lines of integration, is junior cert algebra. This is a nice section, and the good thing is once you master this one, there's 3 other sections and good questions in the Leaving Cert that can be answered without too much more effort. Okay, inertia and movement of a rigid body and the compound pendulum, you know, the kind of ones you see in grandfather's clocks, they're all coming up in the next talk that we will have here. Okay, bye now.